Hi, Assalamualaikum. My name is Muhammad Adi Ahlami bin Talmizi. We are from Group 5, represent Cooling Tower. So here our group member is Muhammad Adi Ahlami bin Talmizi. The second one is Muhammad Izzuddin bin Zamli. The third one is Muhammad Hidayat bin Azri. The fourth is Muhammad Azmir bin Yunus. And the last one is Muhammad Harith Sufian bin Muhammad Zulkifli. So let's go to the first presenter. Hi, Assalamualaikum. My name is Muhammad Adi Ahlami bin Talmizi. My metric number is TD220091. So I will continue the presentation with introduction. So in a power plant, a cooling tower works to remove heat from water that has been heated by industrial operation and equipment. So cooling tower receive hot water from the industrial process and release the cold water, which is then recycled into the industrial process. There are two cooling tower that are often used in power plant, namely cross flow cooling tower and counter flow cooling tower. So we will talk about cross flow cooling tower first. So as we can see here at the above, we have cross flow cooling tower. So cross flow cooling tower airflow horizontally over falling water while water flow vertically through the filling media. It's called cross flow because air and water both pass through it. So a special cross flow method eliminates the need of air through the what we call it gearbox system. This causes the hot water to flow by gravity and into a waste container located on the roof of the tower before the medium is filled. All units are connected to a disposal vessel which has a typically cross flow cooling tower layout. So we will go to the second cooling tower, which is counter flow cooling tower. So flow of water in the filling media causes the water in the counter flow cooling tower to flow vertically upward. It is not realistic to accept container gravity flow as in a cross flow cooling tower system because the airflow in a counter flow cooling tower system move vertically. Therefore, pressurized spray technique usually of the pipe type of the use by counterflow cooling tower system to spray water to the top of the fill media to correct the situation. The pipe and nozzle of this cooling tower are often spaced apart to avoid airflow obstruction. Okay, so I think that's all from me. I will pass to the next presenter. Thank you.
This is the theory of cooling tower. Cooling towers are important in industrial and power plant for efficiently managing heat from machinery. The heat transfer process in this tower follow basic principle which is radiation, convection and conduction. Equipment like condenser and heat exchanger generate heat during industrial process requiring effective cooling system. Water from the industrial process cools down in the tower through evaporation, spreading across cooling tower fill material. This creates a large surface area for efficient heat exchange with surrounding air. Forced or induced air circulation in the tower enhances the evaporation process. There are two types of cooling towers, mechanical draft and natural draft. Key performance parameters include wet bulb temperature and approach temperature. Proper water treatment is crucial for preventing scaling, fouling, and corrosion, ensuring effective heat transmission. Regular monitoring and maintenance are essential for optimal efficiency. Understanding cooling tower heat transfer theory is important for efficient heat dissipation in industrial setting. This is the method that we use in this project. The first is problem identification. The issues of heat loss in the pipe leading to the cooling tower needs to be clearly defined. Second is data collection. Gather pertinent information on the pipe system of the cooling tower such as pipe diameters, insulation requirement, operating temperatures and surrounding environmental factors. Third is installation assessment. Examine how well the pipe installation is holding up. Look for cracks, damage or potential insulating gap. Make sure that the installation material is appropriate for the temperatures being used. Next is heat loss calculation. To find out how much energy is being lost through the pipes, calculate the heat loss. Next is develop solution. Take into account changing or adding insulation, increasing the amount of insulation covered and fixing any problem in the structure of design. Last one is implementation. After making the necessary adjustment, put the chosen solution into practice and closely watch how the pipe system functions.
Hi, my name is Muhammad Ida bin Azri, and now I'm going to tell you about problem 1. Water from production enters the cooling tower at the temperature 200 degrees C in a carbon steel pipe K equal to 80, whose inner and outer diameter are D1 equal to 4 cm and D2 equal to 4.5 cm. The pipe is covered with 2 cm thick glass wool insulation with K equal to 0.05. Heat is lost to the surroundings at temperature 10 degrees C by natural convection and radiation with a combined heat transfer coefficient of H2 equal to 20, taking that heat transfer coefficient inside the pipe to be H1 equal to 58. For the calculation, you need to find the area first. For area 1, you use the formula 2 pi R1L. R, you need to find it by dividing the diameter 1 divided by 2, and for A3, use the same formula 2 pi R3L. R3, you need to find it by diameter 2 divided by 2 and plus 2 for insulation. Individual thermal resistance become Ri equal to R convection, and the formula is 1 over H1 A1. And for R1, R pi equal to ln multiplied by R2 divided by R1 and divided 2 pi K1H and K1L. And for R2 equal to R insulation, same formula, ln equal to ln multiplied by R3 over R2 and divided by 2 pi K2L. For R outer, R convection, use formula 1 over H2 A3. And then R total uh, plus all the Ri plus R1 plus R2 and plus Ro. And then Q dot and temperature infinity minus temperature over R total. And then for temperature difference pipe equal to Q dot pipe. And then for uh, temperature difference for insulation, Q dot insulation. And then you got the answer. That's all. Okay, for problem 2, all the information is same as problem 1 and just one difference, and it is the pipe is covered with 4 cm thick glasses wool insulation, and all the calculation is quite similar with problem 1. For calculation for question 2 is the difference at A3. We use R3 equal to diameter 2 divided by 2, and then we plus 4 because the insulation is 4, not 2. Okay, and then for R2, R insulation, uh, the result will be a little bit different because we use R3. And then RO also the same. The result becomes a little bit different because of insulation at A3. And for R total, same formula, Ri plus R1 plus R2 and plus RO. And for Q dot, temperature infinity minus temperature and then divided by R total. And for temperature difference pipe, we use Q dot R pipe. And then for difference temperature for insulation, we use QR insulation. And that's all.
Okay, hello. My name is Muhammad Izzuddin. Today I'm excited to share about discussion into our thermal infrastructure, specifically focusing on the distinct property of two pipe and how their careful selection can significantly impact our cooling system efficiency. So, point one, distinct thermal properties. Our exploration begin with the recognition that our two pipe exhibit remarkable different in their thermal insulation qualities. First pipe, suction process. Moving on to our first pipe, which is possess a higher heat loss. This characteristic made it particularly suitable for suction process, especially in the realm of cooling tower operation. That the enhanced heat dissipation it offers accelerate our cooling process, ultimately contribute to more efficient system. So for the second part, we have a discharge application. On the other hand, our second part, which is relatively smaller heat loss, proves to be an intelligent choice for system discharge application. By minimizing heat loss during liquid addition, we can effectively preserve lower temperature thereby through reducing heat generation and improving overall energy efficiency. So, customized selection for efficiency. This brings us to crucial consideration, the importance of tailoring our pipe selection to specific thermal properties. A customized approach ensure optimal performance aligned with our operational needs. So, energy efficiency and cost reduction. In essence, this carefully evaluation of insulating qualities not only satisfy our cooling requirement but also translate into tangible benefit. It reduce energy consumption and subsequently our operating cost, which is particularly significant in our educational context. Conclusion. As we conclude, let's the between thermal properties and operational needs. Our deliberate pipe selection isn't just about material, it's about strategic move toward a more energy efficiency and cost effective cooling system. Thank you. And
For the conclusion, my name is Muhammad Sufyan bin Muhammad Zulkifli, and my manager's ID is DD220090. I will continue for the conclusion. For the convection and conduction are essential in heat transfer process with cooling tower. We know we play a crucial role in dissipating heat from industry process. Natural and forced convection contribute to the removal of heat, with natural convection occurring as warm air rise, creating airflow within the tower, while forced convection is driven by the fans that enhance heat transfer rates. The efficiency of convective heat transfer is influenced by factors such as air and water flow rates, ambient conditions, and the design of the tower. Properly designed cooling tower optimize convective heat transfer for effective cooling. Heat hence infill media within cooling tower enhance convective heat transfer by increasing the surface area for contact between air and water. Water cascading over the field facilitates heat enhanced exchange through convective process. Next, we go to with the recommendation. For the first item, we focus for material upgrades. In material upgrade, we need use the high performance material for pipes for enhance the thermal conductivity and corrosion resistance in the cooling tower. Next, insulation enhancement. To evaluate and upgrade insulation system to minimize heat conduction loss. Next, computational modeling. Use CFD and heat transfer simulation to optimize pipe design and identify improvement areas. Next, flow distribution analysis. Conduct through analysis of water distribution to ensure uniform cooling. And next, periodic system audit. Identify and address issue impacting heat transfer efficiency. And lastly, upgrade controls. Enable adapting adjustment to varying operating condition and optimize heat transfer process based on real data. That's all from me.
That's all from Group 5. Thank you.